There's a lot of ways to get to the answers that are here, but there are a lot of wrong answers out there too. So let's start with the easiest problem I gave you, which was to find the acceleration. Of course, it's positive 4. Good job. You found the slope. That's what the vast majority of you did. But some of you did it another way. Some of you recognized that the initial velocity was negative 8 meters per second. You said maybe the time was 2 seconds with the final velocity being 0, and you solved and found the acceleration that way. Fine. That'll work just fine. Of course it will. V equals AT plus V naught. If I solve this for A, I get delta V over delta T, the definition of slope. It has to work this way. We based everything on this. So any problem with that? Good, good. Now, here's where most of you blew it. It is true that the acceleration is positive 4 meters per second squared. But it's not speeding up or slowing down. It's doing both. For the first 2 seconds, it's slowing down. Starts with a speed of negative 8 meters, starts with a speed of 8 meters per second and goes from 8 meters per second to 0 in the first 2 seconds. That's slowing down, right? The fact that it's going backwards doesn't matter. Slowing down and speeding up is whether the speed is becoming a smaller number or a bigger number. So it slowed down for 2 seconds and then sped up for 3 seconds, right? That's what I see here. That's not what the answers were. Most of you saw the positive and just said speeding up. That's not true. It spent the first 2 minutes slowing down. How far does the object go? Wow, here's where there's a lot of divergence of what I would have expected. How far the object goes is not displacement. It looks to me like in the first 2 seconds, I could figure out the change of position before it came to rest. It was traveling backwards. I could put all those things together. Or I could quite simply remind you that the area here would be the displacement for this first interval when it was coming to rest, which was negative 8 meters. 1/2 base times height. Or plug it into a motion equation. But after that, it traveled in the positive direction for 3 seconds. Well, during those 3 seconds, it got to a speed of 12 meters per second. Somebody last class period asked me how I knew that. Pick a way, right? You have the acceleration. Set your time interval for 5 seconds, your initial velocity for negative 8, and calculate it. Or remember that it's increasing its speed by 4 meters per second each second. From 2 seconds to 3 seconds, it goes to 4 meters per second. From 3 seconds to 4 seconds, it goes from 4 meters per second to 8 meters per second. The velocity is changing. It's increasing by 4 meters per second each second. There's just a lot of ways to get to that answer. But once you know that, this area is 18 meters. How far did it go? 26 meters. Right? 8 meters backwards, and then 18 meters forwards. That's 26 meters. But what was its displacement? Well, I just add these two numbers together and get 10 meters. Or I change this to 5 seconds and find out the displacement and ignore that. There's a multitude of ways you could have found your answers. So here's the thing. None of this is hard. None of it. But you don't know to do it. Some of you do, about 50%. If this had been your quiz, a lot of people in this room would be asking about when's the retake. This is all the stuff that's in your test, by the way. Problems, graphs, all in there. But here, boy, I saw some weird stuff here. I saw some really weird stuff. We're starting from the origin. The slope is negative and travels in the negative direction. I know at the 2 second mark that the object is stopped. So I know the curve has to curve in such a way that it shows 0 slope at 2 seconds. Something like that probably would work. Look, you're going to have to be able to do this. And there should be no surprises about these. For one, x equals 1/2 a t squared plus v naught times t plus x naught. This one had to be quadratic, right? This is position as a function of time. It is quadratic by definition. You can put it in your calculator. Put x naught as 0, put everything else in there. You have all these numbers. And this one's got to be linear. By definition, that's what we've been dealing with. Accelerations that are constant, these are the results. So, the first thing I want to impress upon you is I am going to need some of you to step up. And you guys who got all these right, good job. That's all I'm asking for. So, I said to you at the beginning of this unit that we would eventually have to talk about the difference between instantaneous and average, that these are modifiers, and we have to use these modifiers to describe some of the words. We'll use them to describe velocities and accelerations and positions, average and instantaneous. Everything we've been doing so far this year has been instantaneous, meaning all of this stuff, all these equations, everything that's here has all been based on the idea that we're looking at instantaneous moments, meaning I'm looking for the instantaneous position or the instantaneous velocity. I'm giving you the velocity at a specific instance in time. The word instantaneous means at a specific moment or instance in time. So this object's velocity is changing. Its instantaneous velocity stays a different number all the time. It's always changing. So when we say instantaneous, we mean at a specific moment in time. Average has an entirely different meaning. And for us, we're only going to worry about average velocity for the time, for the whole year. And I don't care too much about this, but I would hate for you to make it out of this class without knowing what average meant here. So average speed and average velocity. These are well-defined ideas, and what I want you to understand by that is they have a specific definition, something that utilizes what we just did earlier today. Both of them are based on the concept of a weighted average, but since the velocities and speeds were always changing, it's hard to find out how to do a weighted average under these circumstances. And I'm not sure you guys even remember what a weighted average is. But a weighted average is a way of dealing with averages when you're trying to look at something that might be changing over time or changing over person to person, depending on what your average is going to be. It's where sometimes something weighs more, weighted, meaning it's more important in the average than other things. Average speed and average velocity are based on the concept of a weighted average. Average speed is defined as the total distance traveled in your time interval. While average velocity is the total displacement over your time interval. That's how they're defined. So be careful. Know what the time interval is. I can give you a graph and ask you what the average speed was for the first 2 seconds. Or they can say from second 1 to 4. Be aware of what the time interval is. Don't be complacent. Don't assume. But for this example, I wanted to show you what it would be if we did the entire time interval that we observed. We observed 5 seconds. And in those 5 seconds, the object traveled 26 meters. That was the total distance it traveled in 5 seconds. 8 meters backwards, 18 meters forwards. For a total distance traveled of 26 meters, its average speed would be 26 divided by 5, right, or about 5.2 meters per second. while its total displacement will be positive 10 meters in 5 seconds, or positive 2 meters per second. What's important to understand is that this probably represents the average speed it was going all of the time, backwards or forwards. So if it went at a constant speed for 5 seconds, it would have to go 5.1 meters per second for 5 seconds to have covered 26 meters. Average velocity would be to replace the object with something that was only moving at 2 meters per second in the positive direction. Without accelerating for 5 seconds, it would have also had a 10-meter displacement. These do not show up hardly at all on the exam, but I want to make sure you have their definitions so that if they do show up, you could employ them. I'd say a multiple choice question or two, perhaps. And usually they're in conjunction with a graph. Any questions about this? 2 straightforward definitions, something else to add to your things you're thinking about? Although you do not have to memorize equations, as people keep asking me, do I have to memorize those? I've tried to make exceptionally clear since the start of this year is that you guys have a lot of math at the ready, a lot of mathematics that you've learned, but you've not necessarily been successful at implementing it all the time and have needed some reminders. So I have spent quite a bit of the beginning of this year helping you with those reminders. That's going to have to come to an end eventually, as I need you to start bringing new things to bear, and I need you to learn new things. So we're going to learn some new things today, and to do so, I need to make sure that the stuff you do have is pretty solid. So we started with this. A velocity graph where there was a constant acceleration. And a position graph that represented the same instant being demonstrated. It looks something like that. All right. These are the 2 graphs. We spent the first 2 weeks showing that these 2 things could produce this group of functions. We started by looking at slopes and areas, and from there we were able to come up with a set of relationships. And we showed that these relationships were true because we put the stuff on the track and we, let it roll down there and took data, and this is what was the product of the data. So I want to be really clear that we proved this using algebra and a little bit of substitution, but not much else. That was really it. Maybe a little geometry, right? You had to have the area of a trapezoid at the ready, but that was really all we needed to do to kind of prove that these things could produce a set of functions. Today I want to show you the calculus behind these functions. Calculus does this in a far more elegant way. But to understand the calculus, you're going to have to learn new math. Now, I've got a few people in this room who have had calculus. Raise your hands. I have a few people in the room who are taking calculus currently. Raise your hands. And I have a few people in the room who are not in calculus at all. That would be the rest of you. Calculus right now is in the middle of, calculus AB, and maybe even BC, is in the middle of talking about limits. In AB, they've been doing limits for a long time. People are getting tired of it. Pretty soon, you're going to learn the fundamental theorem of calculus, which is a limit minus a limit divided by a limit, which is why you're doing nothing but limits right now. And I promise, all the things I'm going to show you at one time or another will be presented to you in calculus to prove that they work. You'll put this stuff into the fundamental theorem of calculus, and it'll spit out the answers you're about to see. I want you to understand that for the most part in this room, the calculus is the black box. What I'm going to be teaching you is a procedure, a kind of like a function, but it's not. It's a little different than that. I want to start with something that you already know or are supposed to know. The slope of a velocity versus time graph is acceleration. We defined it that way. And velocity is the slope of a position versus time graph. Now, the slope of the velocity graph is pretty straightforward because it's already a straight line. We've been dealing with constant accelerations. What we're going to learn today is a method that will allow us to deal with any kind of acceleration, even accelerations that aren't constant. where the acceleration is changing. That's what we need to learn today, is what these things can be, what we can do to these things to make them more functional for things that aren't just a constant. But I want to show you that they work by focusing on what we know. Does that make sense? So we're going to focus on this so that you can see how it works, and then we're going to apply it to situations that don't look like this. First, is it possible to take the slope of this graph? We talked about how to do it. Is the slope ever the same? No, it doesn't look like it. The slope looks like it's always changing. We know that that has to be true because if you look over here, is the velocity ever the same number? No, the speeds are, right? There's some places where the speeds are the same. Like I have negative 8 meters per second here. I probably have a positive 8 meters per second there. There's a time where I'm traveling the same speed, but am I ever traveling the same velocity anywhere on that graph? Which means on this graph, I never have the same slope. Every single point on this graph has a different slope. We talked about how you could find a slope at one of these points. We said that you could take and draw in a tangent line and find the slope of that tangent line. And that means you could use this change in x over change in y to figure out, change in y over change in x, use this function, the slope function, to figure out the slope at a point. That's not particularly elegant. There are other ways to find the slope. In fact, that's what calculus is about. Since the slope changes all the time here, there is a function that must describe the slopes. So calculus is a way of creating a new function from an old function. This new function will describe the slopes of the old function. That's what calculus is about. And that's where it starts. To understand this, the first thing we have to do is kind of change the way we're going to talk about these ratios, these fractions. So the first thing I'm going to do is I'm going to write them in a different form. I'm going to replace the deltas with d's. This is a symbology that's going to alert the reader that we're talking about a derivative. Now, for those of you who think you know something about calculus, good. Be that person. Be the person who knows something about it. But for you guys who don't, this is still a fraction. In the same way, this is a fraction. And it's important that you understand that it's just a fraction because later this year, we're going to create differential equations and solve them. And you're not going to do that in your calculus class. So I need you to know that we're going to do things that aren't in your calculus class. But you have to be familiar with the symbology. This symbology still indicates that we're looking at a fraction. It's a rate of change. It's the change in x related to the change in t. The same way that this says the same thing. The d, though, means that we're dealing with a very small incremental change in time. That's what the symbol means, that we're looking at a very small change in time. For this, we could take any 2 points on the line. Over here, we're saying the 2 points are incredibly close together because that will give us the best estimate of what the slope is. Calculus takes us to the extreme, the limit where dt is as small as possible. That's why you're doing limits in calculus so much. But that still means that this is a small piece of length, and this is a small bit of time. And this is a small change in velocity, and this is a small change in time. So you can treat it like a fraction. I can multiply both sides of this fraction by dt and get dx, a small length, equals the velocity times a small change in time. I can treat it just like an equation. These are just two numbers being multiplied together, a velocity and a small length. And it gives me, a velocity and a small time. And this gives me a small distance. Okay, it can be treated just like that. That's the first thing I want you to know about this symbology. The second thing I want you to know about the symbology is that this can be written as an operation. Although these are functionally the same, by writing it this way, I'm telling you something different. I'm writing it as an operation. You see, an operation can be done to both sides of an equation. Meaning, just like you can square both sides of an equation, and you can raise both sides to the same base, or take the logarithm of both sides of an equation, you can take the derivative of both sides of an equation. So we can treat it like an operation in algebra. Now, the way this would be spoken, if you were to speak this out loud and wanted to read this equation to somebody, you would say this part first. Take the derivative with respect to, that's the bottom part, respect to time. You would say time here because t is in the denominator. So that first part says to take the derivative with respect to time. This part is the function. So if I was to read this to you, I would say velocity is taking the derivative with respect to time of the position function. That's how you would read that sentence. As a mathematical sentence goes, it's important. Now, there are lots of different things that go here. Every function has a means of taking its derivative. Every function. Trig functions, logarithm functions, exponential functions, they all have a way of taking a derivative. They're not all the same. And most people who take calculus end up memorizing most of the different kinds of derivatives that there are because they're not particularly hard to memorize. And a lot of them are repeated. But every function has a derivative. What you learn in calculus are all the different ways of taking derivatives of more and more complicated functions. That will be the first half of your experience. The second half will be going the opposite direction, taking the antiderivative of all sorts of different functions. That is essentially most of calculus. The difference, you prove it. You have to do it the hard way, the long way. We're going to skip that. I let calculus do that part. I want you to know the functional answer. So we're going to learn one type of derivative today, the polynomial function. Do you guys know what polynomials are? Good, you should. You're supposed to. So we're going to talk about taking the derivative of the polynomial function. You will have to learn 4 different functions in here. How to take the derivative of a polynomial, a trig function, the logarithm function, and the exponential function. You have to know those 4. And those are the 4 we'll learn in here. Only polynomials for the next 6 months. So you got lots of time. First, I want to use a function that we already know. This is the function I want to use. This is our actual polynomial function. All I've done is take the x minus x naught displacement and separated it to make a function and to turn it into a polynomial. This is a polynomial effectively about t. Now, we're going to do the polynomial function, but before I get into it, you need to know how to take the derivative of a polynomial. So I'm going to slide over here into a blank space, and I want to talk about taking the derivative of a polynomial. So I'm going to create a polynomial. My polynomial is b times c to the n power. Okay, so again, notes. Take the derivative with respect to c of this function. So here's what all of those things mean. Thing number 1, taking the derivative. We're going to do an operation. With respect to c, c becomes the important variable. It's the polynomial variable. Everything else is a constant and can be ignored. Let me say that again. When we say with respect to c, c becomes the functional variable. Everything else in the function can be ignored. They're constants. So if I take the derivative with respect to b, you'll get a different answer. All good so far? Step one, if it's a polynomial, and I've identified that it is because it's a coefficient times a functional variable raised to an exponent. That's a polynomial. It's only one nomial, so I could say it's a mononomial, but it's still a polynomial. If I had several of these, then they would be poly. The operation to take the derivative starts by you taking out the constant and placing it outside. The derivative is distributable. So I pull the constant out and I apply the derivative to the functional variable. Now, this is a straightforward function, so I follow the polynomial rule. And the polynomial rule is this. You take the exponent and place it out front. You then take one away from the exponent. Then you simplify. That's all there is. That is taking the derivative of a polynomial. You put the constant out front, you take one from you pull the exponent down, and then take one from the exponent. That's the whole process. Now, we're going to apply this, but does everybody have this down? This is the polynomial derivative. Last class, I switched screens too quick. I'm just wasting time writing all this down. So, we are going to take the derivative with respect to t. I'm going to take the derivative with respect to t of the function x, which means I'm going to take the derivative with respect to t of this function. T is the functional variable, it's in the denominator. We already defined the left. The left is dx dt. That's defined as velocity. I have a function for position. When I take the derivative of that function, I get the velocity. Okay so far? I distribute, but I ignore the constants. The constants come out front. These all have constants. The problem is the last one. The last one doesn't appear to have t. If you have a polynomial and you're missing t, or you're missing the functional variable, put it in there. This is t to the 0 power. Right? What is t to the 0 power? Just like t by itself is t to the 1 power. So don't be fooled. That's stuff you should know. It's okay. Now I have the same functional variable in every one of the nomials. So I'm going to distribute my derivative function, or operator. So I've distributed my derivative. Are we good so far? Remember the process. I bring down the exponent and I subtract 1 from the exponent. So all right, so I did the first one, right? Brought the 2 down out front, subtracted 1 from the exponent. We all good? Any questions? Bring the 1 out front. Bring the 0 out front. All right, we have taken the derivative. Now simplify. So 1/2 a times 2, just a. What's t to the 2 minus 1? Just t. All right, moving right along. Plus, what's v naught times 1? T to the 1 minus 1. It's just 1, right? It's t to the 0 power. So just 1. I'm going to leave it like that. And do you realize the last one disappears? Right? Because 0 times anything makes it disappear. So we're done. We took the derivative. And what did it produce? The straight line slope formula. Exactly what we would expect it to produce. Okay? Now, if you take the derivative of this function with respect to time, do you see what you get? You should. You should try it. Because you'll find out you get just a, because it's a constant. You should practice. This is taking the derivative. This is how Newton actually did this stuff. Taking the derivative and taking the antiderivative. The antiderivative is this process backwards. And some of you probably can already do that by just looking at it and doing the process backwards. Adding one instead of subtracting one, stuff like that. But you need to be able to go in both directions. We're going to learn to take the derivative and the antiderivative. That's what we're going to do tomorrow. We're going to practice. I want you to see, though, that this is the functional equation for all of the slopes. So if I wanted to find a slope at time t, I take the derivative of my position function, and I get a new function that is full of velocities, all the slopes. So started there, got there, did it with one process, didn't even need a graph for it. So it's very elegant. We'll learn that there's lots of different derivative functions. So you guys in calculus, you know a bunch of them, right? For example, the derivative with respect to t of sine of t. There's a function here. Again, if you ask them why this is true, nobody in calculus can tell you, but the answer is cosine. Again, if you ask them, they won't be able to tell you why that's true. They could not put that into the fundamental theorem of calculus and tell you why it's true, but it is. Same with like this. This one will blow your mind. These are the derivatives. You know one. All right, you've done one now. You will learn a group of them. And once you know the group, oh, by the way, all of these, they're on the equation sheet. They give you all the derivatives you will ever have to know. I would not want to be looking at the equation sheet for these. Some of these are, you want the process fast. We're going to do nothing but practice tomorrow.